Gamma ray bursts are extraordinarily bright. They're the brightest things in the universe since the Big Bang. And they were first discovered in an unusual way, as a consequence of the Cold War. In 1963, the Nuclear Test Ban Treaty was signed. However, the USA suspected that the USSR might attempt to conduct nuclear weapons tests in space, especially behind the moon. So they launched satellites known as the Vela satellites, which is short for Velador, meaning watchman in Spanish, which could detect the gamma rays that would be released in a nuclear weapons test. In 1967, the Vela satellites detected a gamma ray signal which was obviously not from weapons testing. Although it was unclear what had happened, it wasn't considered important and the information was filed away. 6 years and many gamma ray bursts later, in 1973, the information recorded was released and the astronomical research community set about finding out more about them. I asked Professor Julian Osborne to tell me more about gamma ray bursts.
Early on, gamma ray bursts were rather poorly studied, and so there were thousands of ideas about what caused them. With more data, the number has reduced. But I mean, the truth is we've only learned the distance to gamma ray bursts in the last decade or so. So it's a very young science.
Mm-hmm. There are two types of gamma ray bursts, short duration and long duration. And it's still quite unclear what causes these gamma ray bursts, but it's thought that long duration ones, which last for over 2 seconds, are associated with the death of a massive star, core collapse supernovae, and the birth of a new black hole.
The long ones are typically said to be longer than 2 seconds, maybe up to, I don't know, up to 1,000 seconds or something, although they're rarely that long. And they're probably due to the collapse of a massive star. So if that star is rotating, then the hypothesis is that a jet is formed as part of the process of the collapse of that star, and that jet penetrates the collapsing atmosphere of the star, and when it does so, its internal energy allows it to be accelerated to very close to the speed of light, and if that jet is pointing towards us, then we can see it as a gamma ray burst.
Short duration gamma ray bursts are less common and are therefore less well studied, but they're thought to arise from the merger of either two neutron stars or a neutron star and a black hole, leading either to a new black hole or a more massive black hole.
So for short GRBs, those shorter than a couple of seconds, those probably occur due to the collision of two neutron stars, perhaps the collision of a neutron star and a black hole. Now, these are small objects and they're not just going to collide free wandering through space, but this can certainly envisage scenarios in which a binary star ends up consisting of two neutron stars in a close orbit around each other. And due to the emission of gravitational radiation, that orbit gradually shrinks until they make contact, and so they're spinning up as they get closer and closer and closer, and eventually collide. And so again, you've got an axis of rotation and a very energetic collision, and so you can get a powerful jet pointing towards us, and again, that's probably what happens for the short GRBs.
Right. The amount of energy released in these gamma ray bursts is staggering. They release the same amount of energy as the sun releases over about 8 billion years.
A lot of energy. There's no unit of energy that I can put it in which isn't a vast string of zeros. Okay. So it's a lot of energy.
Because gamma ray bursts are so bright, they can be seen at extremely large distances. But because the light takes time to travel from the burst to us, looking at the burst is like looking back in time. In fact, one of the gamma ray bursts astronomers have detected exploded about 13 billion years ago. That's only about 700 million years after the Big Bang. So these gamma ray bursts can bring us information about the far distant past. But how do they produce the gamma rays that we see?
So The first model for the emission of gamma rays was that in this jet you have both fast and slow material, and so the first ejection or the early part of the jet might slow down by collision with stuff, and then later material might still be going at full speed, it would collide with it, and it's that sort of internal collision within the jet which is thought to give rise to the gamma rays.
It's not just gamma ray telescopes that want to look at gamma ray bursts. After the initial gamma rays, other kinds of light, visible for example, are released as well, and this is called the afterglow, and it can help us to understand more about the burst. I asked Julian how easy it is to observe gamma ray bursts.
Well, with the right kit, very easy, but without it, impossible. So the question is, how do we really detect them? And the answer is you need an instrument that has a wide field of view, because they're rare and you can't predict them. So Swift, for example, detects about 100 gamma ray bursts a year, and as I said, they can come from anywhere in the sky. So Swift has a so-called burst alert telescope, which has a field of vision which is about similar to the human eye. So if you just close one eye and look at the sky, that's roughly what this burst alert telescope can see at any one time.
Swift quickly pinpoints gamma ray bursts so that it and other telescopes can quickly point to it and observe it too. Current ground-based gamma ray telescopes haven't been able to detect gamma ray bursts because they're just not sensitive enough, but the CTA should be able to change this.
So it won't see a huge number of gamma ray bursts, but those it does see will give fantastic data. CTA is hugely more sensitive than Fermi for gamma ray bursts, and so it'll be really quite revolutionary when we get one of these things, but it might only be a few a year.